here we go. Okay, so we're going to go back and just quickly review motions of the sun, then we'll move on to motions of the moon, talk about eclipses and a few other interesting things like that. Okay, we've already actually touched on seasons last time, and there's sort of two major things about Earth's motion that you should already have clear at this point. We have Earth orbiting around the sun, right? It experiences 65.24 days of Earth orbit around the sun. So there's an axis to Earth's orbit around the sun. I mean, the orbit is like a disk, and there's an axis that sticks out of the disk, right? Like an axle or something like that. That's what we call the orbital axis of Earth's orbit around the sun. But the Earth also has a 24-hour spin. So we have two axes. We have the spin axis of the Earth, which is its daily rotational axis, and then we have its orbital axis around the sun. And those axes are not parallel. There's an angle between them of 23.5 degrees. I've already gone through this, but I wanted to reiterate this point. It's that tilt that gives rise to the seasons, because basically the seasons are due to the fact that the sun rises different amounts above the horizon at noon, different times during the year. Noon in the winter, it's noon. You think noon, the sun's high in the sky, but that's not true. Noon is just when the sun is as high as it's going to get in the sky. But in the winter, that's not very high above the horizon. And in the summer, it's much higher. And that's the whole seasonal effect. And it's entirely due to the tilt of the spin axis of the Earth relative to the orbital axis. They were just parallel. Every day would be the same for us. The sun would rise at the same point above the horizon every day. And we'd have just as much heating every day. And there wouldn't be any seasonal effect, because the seasons are completely driven by the different amount of solar illumination that each part of the Earth receives. All right, so anyway, this is also linked with the idea of the celestial sphere, which I've already talked about. The celestial sphere is just a collection of all the stars, basically. And we think of it as a coordinate system because each star has a specific coordinate, which is kind of a latitude longitude system. And I'll get a little bit more into this a little soon, but the entire coordinate system spins around us every 24 hours, just as the stars appear to spin around us. So even though we have stars rising and setting, their coordinates, the celestial coordinates of them, stay the same because the grid of coordinates just moves with the stars. Okay, so again, I've shown this slide before. Somebody fix it. I wanted to kick that for some reason. It just seems like sort of a problem that a good kick would stop. I don't do anything else about that. But okay, so here's our celestial sphere. The significance of this axis right here is that's the spin axis of the Earth. And that's why this red line is called the celestial equator, because it's the projection into space of Earth's equator. And we also have the coordinate system I was talking about. This declination is like latitude. The right ascension, which is in time units, because we want to have units that repeat every 24 hours, since the Earth spins every 24 hours. We have 24 hours of right ascension, which actually acts as a unit of position in the sky. And this entire celestial sphere is spinning, as indicated there, every 24 hours. So a star, let's say a star at 0 declination and 2 hours of right ascension, right there. That's the celestial equator, which is 0 declination. Any point on the celestial equator has 0 declination, just like 0 latitude to the Earth's equator. Okay, so there's a star right there at 2 hours of right ascension and 0 declination. If we wait an hour, it'll shift over to that position right there, but it'll actually still have the same coordinate value. Because what you have to realize is that if there's a star right here and we wait 1 hour, the numbers and the star shift, right? And the numbers themselves are actually going to rotate because the whole coordinate system rotates with the star. So it's just dragged along. So if we actually keep our eyes on that point, we identify a certain star. If we just keep looking at that point in the sky, we won't keep seeing that star because the diurnal motion will take it away, right? But if we wait 24 hours, that star will return, and if we just keep looking in the same direction, 24 hours later, we'll be looking at the same star again. But if we just keep looking at that point, for every hour of the time that goes by, we're seeing objects in that direction that have an extra hour of right ascension, because we're ticking through right ascension values due to the rotation. As long as we keep looking in the same direction all the time. So that's sort of the meaning of the coordinate system. Now here we have the ecliptic, which again is the path of the sun. The reason the ecliptic plane is tilted is because of that 23.5 degree tilt. If it wasn't for that tilt, this blue ecliptic curve would just be exactly the same as the celestial equator curve, and the sun would not be changing its its excursion through the celestial sphere. Okay, so the Earth would be at the center of this sphere, and if we're in the northern hemisphere during winter, the sun is below that celestial equator in the sky. So remember, the celestial equator is an easily observed imaginary line that, you can think of it as a line describing around, well, you can think of it as a big tube, a big cooling, people-looking cooling tube right there, cooling heating tube. That's the celestial equator, okay? So in the winter, and there's specific stars, like those vents up there, let's think of those as specific stars. In the winter, for us, the sun is down there, down where that speaker is. Well, it's not rising very high above the horizon, right? So we're not getting much direct solar heating. If we wait till later during the summer solstice, now if I could do this, I'd rip that speaker out and put it up here. And you see that's above the celestial equator. The celestial equator is still the same line in the sky, still has the same stars I was just talking about, but now the sun's up there. And so we get the direct heating, and that's all that this is really indicating. I can switch to plumbing. It doesn't have to be heating and cooling. Some people can't please everybody doing that lecture. Okay, so as I like to do it, I like to actually think of the Earth's orbit as this flat plane. That's kind of my way of doing it. So I think of the Earth's orbit around the sun as the flat plane. And then this dashed line is actually the celestial equator, and it's hard to see, but there would be an axis like this, which is sort of spin axis. So I like to give the orbit priority and then tilt the spin axis. And I already showed you this, I think it was the last slide from the last lecture. But this just shows you where the sun is in our sky during different points in Earth's year, which is Earth's orbit around the sun, right? So this is kind of like reality down here. The Earth is really moving around the sun. That's what's really happening. But the celestial sphere is a coordinate system that's set up from our viewpoint on Earth. So when we start out at this would basically be the winter solstice again. Here's our spin axis over here. That's the celestial equator. If that were out in the sky, the sun would be below it, clearly, because here we have the celestial equator. We're up here in the northern hemisphere, and the sun's down there below that imaginary line. That's like being below that tube I was talking about before. And we wait later, the vernal equinox in March. The sun now is actually in the celestial equator. It's indicated right there, so it would be right on the tube. And then later on, it rises above, we get the direct heating. And so the motion through the celestial sphere of the sun is just because the celestial sphere's orientation is switching, relative to the sun's location. That's what's really happening, right? We just have this kind of anthropomorphic view of everything, so we use the celestial sphere, but it's just the Earth-based viewpoint for what's actually happening. What's really happening is we just have a tilted spin axis, and so we have the apparent change in the celestial location of the sun. So the sun, as I showed you last time, simply moves through different background constellations. It's in front of different stars during the year because there's a perspective effect as the Earth moves around the sun. Right? So here we have the sun, here we have the Earth. Now, the sun is going to appear to be in different constellations during the year just because of the perspective that the Earth has looking back at the sun. It's going around the sun, so of course the sun's going to be against different background stars. There's a little bit of a connection with astrology because the most significant constellation for everybody is supposed to be the sun sign, which is the constellation the sun is in when you're born. So some people think, well, if you're born in March and you're a Pisces, let's say, oh, I'll go out on my birthday, I'll look up and I'll see, at midnight, I'll see Pisces up there or something. No, it's exactly the opposite because that means that the sun was in Pisces. So if you go out at midnight and your birthday in March and you look up, you're actually looking exactly the opposite direction. Pisces would be way down there on the night side, the daytime side. Okay, so anyway, so the sun marches through the constellations. These are the most significant, so-called significant astrological constellations because those are the sun ones. But the point, from our point of view, the point is that the sun simply moves around and appears to move against different background constellations as it moves along the ecliptic. Just a figment of the fact that the Earth is actually going around the sun. So what this means is that the patterns of constellations you see at night, when we go out at night, of course, are different constellations during the year because when you go out at night, you're going out when the sun's down, so you're seeing the opposite direction from the sun, more or less, at night. So you're not seeing the sun sign constellation, you're looking the opposite direction. But those constellations that are up are a cycle that changes through the year. So we're just heading into getting sort of close to winter now. I guess it's still summer. Got a little ways to go before we get to winter. But Orion is going to be rising later in the year. This is the characteristic hourglass sky that we're familiar with. There's a region down there that's very famous, a star-forming region with a beautiful molecular cloud, and we'll talk about later on in the semester. So this is the southern horizon as seen in winter from the northern hemisphere. So in other words, we're in the northern hemisphere looking south, and that's what we see in the winter. So those are winter constellations. Looking south in the summer, northern hemisphere, we see a whole different set of constellations, Scorpius, Capricorn, starting to set now. Okay, so we have constellations which look like distinct patterns. You know, we even give some cultural significance to some of these shapes. So it looks like they're kind of fixed in important patterns, but really it's just the perspective that we're viewing them from our location in the galaxy. I won't even say Earth because it's more than just Earth. Like you can go anywhere in our solar system and the constellations are still the same. Because when you move around in our solar system, it's a tiny distance compared to the distance of the stars. So you can go out to Jupiter and look around and you'll see the same constellations. You'd have to go hundreds, thousands of astronomical units away before you would start to see the pattern shift. But it would shift if you flew far enough out into space because you'd see them in a different direction. So the pattern would just look completely different. So here we have Orion that looks like this here. The stars in Orion actually have these very different distances from us. And so as we're seeing from the perspective we have right here in the room, we're looking at it kind of perpendicular. It doesn't look anything like our familiar Orion. It looks like, what? Hard to describe too much of that. But so anyway, so the constellations are a perspective effect due to the direction that we're actually viewing these stars. And again, as it indicates here, some of these stars are even up to 1,000 light years away. Meaning they're pretty darn bright stars to be bright in our sky at a distance of 1,000 light years. These are blue giant stars. Very, very bright. And we also see some red stars that are part of Orion. But you notice the red ones tend to be a lot closer than the blue ones. They're all about the same brightness, which is why they're in the constellation. You don't make constellations out of dim stars, you can have bright stars. The nearby ones tend to be the redder ones, and the more distant ones tend to be the bluer ones, because the bluer ones are brighter.